Hello everyone, I'm Janani Jarachandan from University of Louisiana at Lafayette presenting our research AMPS-Inf automatic model partitioning for serverless inference with cost efficiency. Serverless computing is a promising paradigm because of its one-click code deployment simplicity. There are lots of benefits hiding behind that nature. One is it hides the complexity of server management to the users. It offers pay-per-use pricing model with no charge for idle resources. Also, it has the ability of automatic and unlimited scaling of resources to match the user demands. Hence, serverless platforms from cloud providers are widely utilized by various applications. For example, Xcamera is a framework for video encoding. Locus is a serverless analytics system that uses slow, cheap, and fast expensive storage. ML applications like Cyrus focuses on the iterative model training process. Since direct communication between serverless functions is an open research topic, the applications utilize intermediate storage and other services. The growing adoption of machine learning across different fields raised the question of how machine learning applications can exploit serverless computing. The main reasons are the restrictions with serverless function size and the increasing size of neural network models. In particular for inference, the challenge is how serverless functions can handle large and complex models under the deployment package limit. Sample deployment sizes of 2 neural network models with Keras backend on Lambda platform are shown here. Including Keras dependencies, the deployment package overwhelmed the limit of 250 megabytes. Also, when executing the inference job, Lambda needs to store the model parameters and neural network layer outputs within its storage, that is limited to 512 megabytes. Another challenge is how a user can simply make deployment decisions to control their budget without violating a predefined service level objective in terms of query response time. When a neural network model is too large to fit into a serverless function, the natural step is to partition them. However, it encounters several difficulties. The first challenge is, due to the complex structures of today's neural network models, it is not clear how we can choose a specific partition among a gigantic number of possible ones wisely. The second challenge is the coordination between groups of neural network layers and data transmission between them. Then there is a need for intermediate storage to handle the outputs of partitions. The third challenge is how to judiciously allocate the memory size for each partition. Those requirements are to be fulfilled considering budget and service level objective to get a better configuration for cost efficient and timely response. To cope with such complexities, we present our framework AMPS-Inf, which automatically deploys machine learning inference workloads on the serverless platform towards both cost efficiency and timely response. We did motivating experiments to analyze former questions. Serverless inference deployment and configuration consist of Lambda function with serving code, model weights, ML dependency libraries, machine learning model, and resource configuration. We deployed and executed such MobileNet inference on Lambda for different increasing memory blocks. The size of Keras MobileNet is small and we deployed it on a single Lambda. For this one image serving experiment, we can see that the completion time decreases with the increasing memory allocation while the cost is increasing. Increasing memory size beyond the threshold does not bring much decrease in completion time while the memory cost dominates the total cost. We can see such relationship from these observations that guides us to allocate appropriate memory to achieve our desired objective. To identify the benefits of serverless compared to serverful computing and the possibilities of model partitioning in the serverless environment, we performed two separate experiments on a small and large pre-trained models on Lambda. We compared them with two settings of commercial non-serverless solution, Amazon SageMaker. For a single image inference, the resulting figure shows that serverless inference gives great promise of cost saving without degrading the completion performance. Different configuration results implies that the flexibility of resource configuration brings ample space for improving cost efficiency. For the inference of the ResNet 50 model, we partition it across 10 sequential lambda function and used S3 for the data transfer between partitions. We can observe the ample optimization space with the flexibility of model split and the resource configuration. Then we modeled the serverless inference. Consider a pre-trained model with Y layers. We can partition them into different N combinations. A particular combination G can have K lambdas up to some maximum limit. Hence, the integer variable Y is derived as the number of neural network layers of ith lambda in a combination G. Lambda platform provides a limited number of memory blocks. When ith lambda from combination G holds jth memory block, binary variable X will define the memory allocation. Completion time of ith lambda consists of computation and data transfer time. Monetary cost incurred by the lambda depends on execution time, price of its allocated memory, S3 storage and get put costs, and the lambda invocation cost. These are derived as equations on cost and end-to-end inference workflow time. This is our problem formulation of the cost minimization of an inference job. We derived equations for the constraints depend on the platform limitation and our considerations of reducing search space. When the lambda is invoked, the deployment package will be loaded in combination with the dependencies and the handler with serving code. Hence, the first constraint indicates the deployment package size. The temporary memory stores the files of model and weights, the outputs of each neural network layer, and the prediction results from the previous partition. And it indicates the second constraint. Another constraint to cap the number of neural network layers per partition to reduce search space by removing unpromising solutions. Last one is to limit the number of memory blocks to remove infeasible memory options. To explore the complete design space with the flexibility of model split and resource allocation, we formulated the cost minimization problem and proved that it is a mixed integer quadratic programming problem. For more details, please refer our paper. Next, we see the design and implementation details of AMPS-Inf. The user's pre-trained model is given to the optimizer, which solves the mixed integer quadratic programming problem. It generates the best configuration with minimum cost selected from the different combination of model partitions and lambda memory allocations. The coordinator component creates the zipped deployment packages consist of function and weights. Deployment includes adding partition model and ML dependencies to lambda layers. Then coordinator runs the inference job. User will get the final prediction results. This is the full architecture of AMPS-Inf. For our evaluations, we utilized 4 different pre-trained models. In our first set of evaluations for single image inference, SageMaker settings use on-demand instances with the least prices. The uploaded model and weights are converted and stored as assets and variables in S3. For the mobile net inference, AMPS-Inf predicted 2 lambdas. Still, AMPS-Inf shows much improvement in terms of both completion time and monetary cost over Amaze and SageMaker and gave nearly equal results to the single lambda solution. For the 3 large model inference serving, the figures are for model loading time and prediction times separately. AMPS-Inf gives more than 90% of cost reduction compared to SageMaker settings. In our second set of evaluations of single image inference, we compared AMPS-Inf to 3 different baselines. The first baseline holds random configurations. The second uses a heuristic that packs layers from last to top as partitions until it hits the platform limit. The third uses optimal configurations with exhaustive search. AMPS-Inf achieves cost reduction and better performance than the first 2 baselines. With the cost optimal baselines, it shows better performance with less increment or nearly equal costs. We compared AMPS-Inf with the state-of-the-art Surfer. Surfer does not support automatic partition or configuration. Figure clearly demonstrating that our work outperforms Surfer in both reducing completion time and cost. We extend AMPS-Inf for batch inference. We compared it to an existing framework batch which does not support splitting and memory configuration. For a fair comparison, we implemented AMPS-Inf sequence which follows similar sequential batch invocation and everything else alike AMPS-Inf. The results demonstrate the advantages of AMPS-Inf still hold for batch processing. AMPS-Inf is an automated framework for serverless machine learning inference, which gives better configuration solutions and wisely partitioning the large models in a cost-efficient manner with acceptable performance. It is evaluated with 4 pre-trained models compared to Amazon SageMaker and 3 different baselines. AMPS-Inf outperformed the state-of-the-art Surfer in cost and performance. It is extended for the batch inference and compared with an existing system batch and outperformed it. Results demonstrate that AMPS-Inf, by finding the best configuration of lambda type and model partitions, it achieves cost savings up to 98% without degrading the response time performance. AMPS-Inf can be adapted to other cloud providers' serverless platforms with minimal modifications. For more complex models with a single large layer that does not fit into one lambda, we plan to extend the AMPS-Inf by quantizing the weights. Also, we will extend to large batch scales and for other ML platforms. Thanks for listening.